All right, welcome back everyone, and thank you all for joining. We appreciate you taking your time out to monitor this webinar. So we're going to be talking about product effect and phase angles in metal detection. My name is Stan Flory, and I'll be hosting this webinar. We're going to try to keep it light. We're going to try to keep it interesting, and we're going to have some fun with it, hopefully, and hopefully you'll learn something. I know I'll have some fun with it. Okay, so let's move on. We had a few alternate titles for this webinar that we ran through, and I'll run through a couple of them right now. How does a metal detector work? Why doesn't my metal detector detect metal? Why did it work yesterday and not today? Hopefully we're going to be answering some of these questions today. But before we start, there's a brief message I want you to all pay attention to.
This is all going on live, not on film.
That's right. This is a live demonstration. We have a production crew here, and we're going to try to keep things interesting. So special thanks to the production crew, which is Evan, Cameron, and David. They help get things prepared, and they will be involved in the live demonstrations that will be going on a little bit later in the webinar. So because this is live, as I said, something could go wrong. And if it does, I don't know who we're going to blame, but I have an idea. Anyway, let's get started. How does a metal detector work? The basic principle is that when you pass current through a conductor or a copper wire, an electromagnetic field is generated around that conductor. You can see it indicated here in what is known as the right-hand rule. So the blue arrow or the blue copper wire shown on the right-hand side shows the direction of the current, and the red arrows circling show the direction of the electromagnetic field, and this is known as the right-hand rule. So when you see someone giving you the thumbs up, I really don't think they're giving you the thumbs up, but trying to teach you a little bit about physics. So a modern metal detector works using the same principle. When current passes through the transmitter winding of the metal detector and therefore generates an electromagnetic field, and you can see here on these two images, the green wire is the transmitter winding and the blue wires are the receiver windings. So what happens is the transmitter winding, current gets passed through the transmitter winding, generates the electromagnetic field, and it is picked up and monitored by the receiver windings. You may have noticed that many metal detectors are quite heavy and bulky, and the reason is they need to be filled with something very solid. Some companies use epoxy, some companies use concrete, I've heard, but other companies have different technologies for filling the coils. And the reason is you don't want these windings to move. They have to be very stable, and the positioning of them has to be fixed. So looking at a cross-section of a metal detector, you can see that the receiver windings are equally spaced on either side of the transmitter. And you can also see that the electromagnetic field not only is contained within the metal detector coil itself, but it does extend a little bit beyond the openings of the metal detector. And the reason for that, or not the reason for that, but this is why we recommend a metal-free zone when you install a metal detector, because these electromagnetic fields do extend beyond the openings. You can't have, or you don't want to have, any moving metal inside that area because it can still affect the electromagnetic field and give you a false detection. The metal detector electronics measures and compares the voltage on both receiver windings. So when the system is balanced and there's nothing disturbing the electromagnetic fields, there will be equal voltage on both receiver windings, as you can see indicated below. So we replaced, in this image, we replaced the electronics with a simple voltmeter, if you will. When product passes through, or when metal passes through a coil, you can see, if you watch the voltmeter on the bottom, you can see that it affects the field as it passes through the coil. And this, in a nutshell, is how a metal detector works. Of course, there's a lot more to it, which we will get to. So what actually happens when the metal detector when metal passes through the search coil, how does the metal detector know that it's metal? The answer is very simple. It's magic, of course. Actually, it's not magic, it's physics, basic physics. There are two basic phenomena by which the electromagnetic field is affected. The first is called field concentration by ferromagnetism, and the second is called field displacement by eddy current. So we'll take a look at each one of these and explain them a little bit. So field concentration occurs when a ferromagnetic material, like ferrous metals, enter the magnetic field. So there's some examples of ferromagnetic metals, and of course one is iron, and the other is magnetic stainless steel, which is typically 400 series. 400 series is commonly used in factories and manufacturing plants because it can maintain a very sharp edge and it's very strong, but it has a high carbon content, so therefore the phase angle of that product is more similar to iron, and you get a pretty large signal, and it affects the electromagnetic field by field concentration. And so if you take a look at the voltmeter, we'll call it, on the bottom, which is actually the metal detector electronics, you'll see that the coils are balanced. We have equal voltage on either receiver winding. When a ferrous piece of metal enters the electromagnetic field, you will see that the field lines are attracted or concentrated towards that piece of ferrous metal. And what that does is it induces or increases the voltage in the receiver winding, and you will see an offset in voltage. And now you no longer have a balanced field, but you have an offset voltage. So there is a higher voltage on one side than there is on the other, and that's how we can detect that something has affected the electromagnetic field. So again, this was field concentration by ferromagnetism. The next one we'll discuss is field displacement by eddy current. Field displacement occurs when a non-ferrous metal enters, or any non-ferrous material, I should say, enters the electromagnetic field. Again, you can see that the image on the right, the coils are balanced. There's equal voltage on both windings. It doesn't have to be 1 volt. We're just using that as an example. Examples of non-ferrous materials are obviously stainless steel, copper, brass, bronze, aluminum, and anything else that is conductive, such as your product. And this is very important because we're going to talk about this a little bit later on. We're going to focus on it, actually. So some products, not all products, have an effect on a metal detector, and this is the effect that they have, is that they simply resemble these non-ferrous materials. Some difficult ones are meats, cheeses, and any other product that is conductive. If you stick your hand in a metal detector, you will most likely set the metal detector off. So what happens in this case when a non-ferrous material enters the electromagnetic field? You still get an offset in voltage, but this time it just reacts a little bit differently to the electromagnetic field lines. What happens here is the field lines are not attracted or concentrated towards that piece of metal, but what they are doing is they are inducing yet another electromagnetic field within the contamination itself. And these two fields oppose each other, and it expands the electromagnetic field, or actually displaces the field. In any case, there's still an offset in voltage, so we have a different voltage. So these are the two ways a metal detector is affected by contaminations, conductive materials. Now that we know how the different materials affect the magnetic field of a metal detector, how does a metal detector differentiate between the product, which we said can have an effect on the electromagnetic field, and a piece of metal? Remember that your product was listed with the non-ferrous materials. Not all products have an effect on the electromagnetic field, but some do, for sure. Those that do are known to have what is referred to as product effects. So you will hear this term many times when you're discussing metal detection. Product effect is a major concern with metal detection. If your product does not have product effect, then your chances are of detecting smaller pieces of contamination increases because we don't have anything to deal with except for the metal signals themselves. And you'll see this as we move forward and learn a little bit more about how this works. So although your product might have product effect, we still need to be able to detect metal within your product. All modern metal detectors should have the ability to tune out or minimize this product effect and still detect the metal. Here we go again. So how is this done? It's simple. It's magic. Okay, not magic, but again, physics. The electrical signals in the metal detector created by conductive materials passing through the coil are seen as vectors. By definition, a vector is a signal or another quantity like a force. When you learn this in physics, you talk mainly about forces. That has a magnitude and direction. That is the definition of a vector. The magnitude is obviously the strength, signal strength, or the amplitude of the actual signal. The direction would be the angle from a predefined reference point. In this example, you can see that what the magnitude is. It's the strength of the signal, and the direction is the angle from that bottom horizontal line, or the reference. So, in order to manage the signals internally, the metal detector has to break down the vector into its rectangular coordinates. So every vector has an XY coordinate. You can see it in the blue lines on the left and on the bottom of this chart. These are the rectangular coordinates of this signal vector that we're looking at here. This is the amplitude, this is the amplitude on the x-axis, and this is the amplitude on the y-axis. And we know that these are 90 degrees apart. In many metal detectors, the coordination system is referred to as channel A or channel B. Channel A and channel B instead of channel X and Y, but other metal detector companies may call them something different. Doesn't matter because they are always going to be 90 degrees apart. That's important to remember. The angle, which is referenced from channel A in this installation, or I'm sorry, in this example, represents 0 degrees. So if A is 0 degrees, the phase angle is some angle from 0 degrees. And this angle is known as the phase angle. So these so far now are the top 2 points of this webinar, is phase angle and product effect. So we learned what product effect is. It's anything that can affect, or a product, I'm sorry, that can affect the electromagnetic field, much like non-ferrous metals do. And phase angle is a way that we can look at what that signal looks like inside the metal detector. So modern metal detectors use this concept to distinguish metal signal from the product signal. How is this done? You guessed it. It's physics. So it is physics. This is vector addition and vector analysis is a physical property and is typically learned in many physics courses. So we've already demonstrated that the product signal is seen as a vector. in a metal detector. And this is the same product signal we were looking at earlier. So we can simply set the threshold just above the product signals on channel A and channel B, right? This is channel B, so we can set a threshold here in channel A. Now the threshold is actually the sensitivity adjustment that you set in your metal detector. And when a signal crosses or surpasses these thresholds, then the metal detector considers it metal. So can we just set the thresholds just above the product signal on channel A and B? Right. The answer is obviously wrong. We can't do that because if you forget about running your product through the metal detector and now just run a piece of metal through the metal detector, it can have a completely different vector and has nothing to do with the product vector that we just saw, because now you're just running a piece of metal through the metal detector. So it reacts on it the same way. This will have to be broken down into its XY coordinates as well. But when you pass a piece of metal through with the same product that you ran before, you get a completely different signal. The metal detector will not see the product signal plus the metal signal. All it sees at this point is the total signal, which is this green signal here. So even though you have the product and you have the metal inside the metal detector passing through, now at this point, the total signal is the only thing that the metal detector can see. So in this case, the total signal, the product plus metal, is actually smaller than the product signal if we don't make any changes. On X and Y, the product signal was out to here on A and over here on B. So if we set the thresholds as we suggested before, just above channel A and B, there is absolutely no chance we're going to detect this metal with these current settings, because the actual overall signal is smaller than it was with just a product. So the metal came in, added to the product, made the overall signal smaller. So in order to be able to detect this piece of metal, the metal detector needs to make some sort of an adjustment. There's nothing we can do about the individual signal vectors, nor the resultant total signal vectors, nor their orientation. These are physical properties that you cannot change. This product is going to produce the same signal vector every time. This metal will also send the same signal vector, and the total signal will be the same as well. But the one thing we can control is our point of view, or our reference, of how we look at these three images. Or actually, we're only looking at this one at this point. So we define the starting orientation of the coordination system, channel A and B. Since we defined it, we have the ability to modify it. So there's something we have control over, and we can adjust the rectangular coordination system. So by rotating our coordination system and aligning the product signal to channel B, so now our product signal is lined up with our channel B coordinate. Now we have a much better view of this metal, because now it's further away from channel B, but it's along channel A. And if you look, all we're doing, I'm going back and forth here, you can see all we've done is change our coordination system. We have not done anything to the product signals or the metal signals or the total signal. So this phase angle, this is called phase angle adjustment or phase correction. Very important. It's the major premise that makes metal detector work. You have to have this capability, otherwise you'll be fighting product effect. So remember, we said earlier that the product has its own signal vector or its own magnitude and direction. Part of the teaching process in a good metal detector, or in a modern metal detector, is to pass your good product, good clean product, known to have no metal in it, through the metal detector several times. Every manufacturer has a different process, but basically they're all doing the same thing. You need to learn what a good product signal looks like. and that is represented here in this image to the left. We've run, well, theoretically, we've run product signal through and this is what it looks like. So we have now, the metal detector knows we have a certain phase angle and then certain rectangular coordinates and a certain amplitude on this product signal. When you're setting up a product, especially difficult products, with your metal detector, you're going to need to run at one point or another good product through the machine so that the metal detector can teach itself. Once we know the phase angle, the metal detector will rotate the coordination system accordingly. So my experience is that the metal detectors typically do a better job at this than I can do manually. There are usually manual adjustments where you can override and try to fine tune the phase angle, but I believe that the algorithms that they have in the metal detectors do a much better job and do it efficiently. So now we can set our thresholds just beyond the product signal as we attempted to do in the previous slides. So now we're going to set our thresholds here. So any signal that crosses those thresholds is going to be considered metal. When metal is added now, the same metal to the same product is added, you can see that the resultant vector, that green signal, went way beyond this channel A sensitivity line. And now the metal detector can see this metal inside this product. So we've done nothing to the product signals or the metal signals because we have no control over that. It is what it is. The only thing we can do is change our point of view or how we look at these signals. And that is called phase correction. And so now the metal will be detected. All right, coming up next, we're going to do a live demonstration with some actual product. So we're going to send the boys to the refrigerator to grab a test product, and then we're going to run it through the machine. We're going to show you what the signals look like, and then show you how the phase angle affects the performance of the metal detector, or what you would see on a screen when you run these products. So first, let's get the guys to grab a product.
Hey, wait a minute. Don't you want that package you put in my icebox? What is it? Worms! You put worms in my icebox?
Well, there you have it. I guess we're going to be running with worms. So we're going to set up some demos with our demo worm product, and we're going to have a little fun here. So this is what's happening now. We're going to run some sample product through the metal detector, and you can see here in this image the same image as we showed you before. If you look at the voltmeter on the bottom, you can see it changes as the conductive product runs through the metal detector. So now we're going to go live. We're going to be looking now at the live screen of the metal detector to see what these signals look like. And so right now we're going to have them just run some good product through. Okay. So this is what the signal looks like in a metal detector. This particular screen that we're looking at, I prefer it. It's the signal recorder. The metal detector, this metal detector, we can choose between different graphics. This is really the same information. This black line here is the threshold line, so you can see that none of these products are crossing the threshold line. The top half of this will be channel A, the bottom half will be channel B. So you can look, now we're going to add some actual metal contamination to the product and run it through a couple times so you can see the difference between the signals. So now he's running the same product of worms, by the way. You can see worms up here. So he put a piece of metal on it, a test piece of metal, and now you can see that the signal went well beyond the threshold line, and therefore the metal is detected. We're gonna continue to do that. I'm gonna change the graphic. So now you can see, Dave, put a good one on first. We're gonna see what a good product looks like. It does not cross the threshold lines. We want that signal to be well within. And when you set your product up and you set your thresholds, you don't ever want the product signal to be too close to the threshold. You can see here you have about 50% of product signal to 50% empty space as related to the threshold lines. Now go ahead and put the metal on it. Now we're going to run it again with a piece of metal, and you can see that the difference is going to be significant. So this is a typical way that the metal detectors should work. You don't ever want the product signal too close to the threshold lines. Okay, the next demonstration we're going to do is I'm going to demonstrate how your product, because it has product effect, can have a significant effect on the metal detector day by day. One of the proposed titles we had was, why did this metal detector work yesterday and it's not working today? The reason is your formulation could change in a slight way, but have a huge effect on the metal detector. And that's why it's very important that you have significant separation between your product signals and your thresholds. So what we're going to do now is we're going to put the clean product through, the same product we were running our can of worms, if you will. And you can see that the signal is well below the threshold lines. And now we're going to run the exact same product that we made a slight modification to in its formulation, and we're going to see what that does to the signal. Huge. Okay, so it's the same product, and we're running the same product through the metal detector, and we made a very slight modification to the second product. Okay, they're obviously not worms, so we're going to switch back now, and we're going to show you what we actually did to create these products. And we have a small video. The product wasn't worms, it's actually just a little tub of water. So we filled 2 containers, each with this exact same amount of water, and then ran them through, and you can see the signals are exactly what they were in this video. And then we took a little bit of salt. I don't know if this is a pinch of salt or a dash of salt, but it's a tiny amount of salt. And when you put that one through, you can see that the signal is tremendous. So your product variation from day to day or from batch to batch will have a tremendous effect on how your metal detector performs. And that was the answer to the other question, why does my metal detector work great one day and not the next day, or from batch to batch for that matter? The phase angle adjustment is very important, and it's very important to understand that a slight variation in your product can have a significant effect on the metal detector and would have to therefore be readjusted and maybe come up with a new phase angle. Okay, well, I'm sure this webinar will become available in some other form, so hopefully I'll get a chance to watch it myself. I hope you enjoyed it. I tried to keep it light. I didn't want you all falling asleep on me. Until next time, I appreciate you joining, and thank you for your attention.